All right, we're going to look at linear motion. And when you're studying physics, it's nice to look at motion in just one plane instead of looking at complex motion. If you take it apart into just one direction, we can study it and then get some basic understanding of motion. And then we can apply that to more complex motion later on. So today we're going to learn just the difference between speed and velocity. We're going to talk about acceleration and the relationship when you put those things together, distance, velocity, and acceleration. And then we're going to talk about free fall, any kind of falling motion. And then, of course, we're going to be talking about gravity when we talk about free fall. All right, when we look at speed, speed is just how fast you're going in a car. Very typically, we talk about miles per hour. I'm going 65 miles per hour. That's how fast I'm traveling. So that gives us a distance, the miles, and then per hour means that it's going to be over the time. So it's going to be distance over time, and that's miles per hour. We can make that kilometers per second. We can make that meters per minute. We can make those units anything we want as long as we are careful with our units and make sure that they're the ones we want in our answer. If we're doing seconds, meters per second, just be careful with your units. But speed will be the distance traveled over the time it takes for you to travel that distance. Okay, so we can just rearrange that previous slide formula there that had velocity is distance over time, and we can find that distance then equals the speed times the time. So if you're going 60 miles per hour and you go for 1 hour, you've gone 60 miles. If you're going 60 miles per hour and you've gone for 2 hours, you've gone 120 miles. And I'm sure you guys have done that math in your head on long road trips when you're driving and you know it's 120 miles away. Well, how fast are we going? How long? Are we there yet, Mom? Type of thing. You can figure out approximately how long it is before you get there. The example they give here is if you're going 30 miles an hour and you go for 2 hours, you've gone 60 miles. The only thing you have to do is be careful of your units, right? So make sure if you're measuring in miles per hour that you are looking at how many hours you have gone, not minutes. Don't do, okay, well, it's 120 minutes, I'll multiply by that. You got to be careful with your units, but I'm probably going to repeat that all year for every single unit we do, so. All right, so here we go. What is the average speed of a cheetah that sprints 100 meters in 4 seconds? All right, how about if it's 50 meters in 2 seconds? And I hope you can see here that those would be the same thing, right? You have the distance over the time. We could take that down to 25 meters per second if we wanted our answer in meters per second. You can convert that to kilometers per hour if you wanted to have some fun with the math. Okay. Now let's do an average car speed of 100 kilometers per hour. How fast does it travel in 60 minutes? All right, so 60 minutes is 1 hour. If you want your answer in kilometers, that math is very easy. Okay, so when we look at average versus instantaneous speed, we have to distinguish those. So if I say I'm traveling from here to school, or better yet, my son says he's traveling from here to the high school, and he says, well, it takes him 17 minutes to get there, and it's only whatever it is, 17 miles away. So really he's averaging 60 miles an hour. So that doesn't sound too bad until you realize that he's had to come to a couple stop signs and been going 0 miles an hour, which means when he's on the freeway, he's got to be doing like 70 to average out to 60. So anyway, enough of that. An average is going to be the total time that you have gone and the total distance, and you just divide. So that's pretty easy. Then we can talk about instantaneous speed, and that's the speed you're going at any 1 second during, really you take the time down to a limit of 0, but we fortunately don't have to do calculus in this class. So when you look at instantaneous speed, it'll just be, think of it like that second. Okay, so when we do average speed, 30 miles per hour on a trip from school to home. All right, the instantaneous speed is going to vary. Like I said, it'll be given by your speedometer. And I love the little comment in blue at the bottom. Okay, so which balls wins the race, A or B? And we're going to talk more about energy later, but basically these are going to get there at the same time. So let's look at the average speed. Well, if they're going to get there at the same time, the average speed is going to be about the same. Or I should say the same. But we can look at B and see that as it comes down the slope, it's actually going to have a faster speed, an instantaneous speed right here. It's going to be going instantaneously faster than the A ball. All right, but when we get over here and it has to go back up, it's now going slower. All right, so they may average out the same, but B is going to speed up here and it's going to slow down here. All right. So, car has an average speed, yeah, this is my son's car, of 60 miles per hour. Is it possible for the instantaneous speed to always be less than 60 miles an hour? Ha! Yeah, we all know the answer to that one. All right, velocity is speed and direction of an object's motion. So we've been talking about speed. Now, velocity is a vector quantity, right? We talked about vectors. You have to have the magnitude, but you also have direction here. So as long as we give our speed a direction, we now have velocity. I'm going 30 miles an hour north to Cloverdale. I've now given you velocity. 25 meters per second down, that's velocity. We've given it a direction. Okay, so we can be more specific with velocity. It is very similar to speed, but there is an important distinction when we talk about velocity, because as we add them, it's going to be important if you have two cars going, are they going 60 miles an hour both in the same direction, or are they going 60 miles an hour into a head-on collision, one going the opposite direction? And with velocity, we can see that difference. Okay, so the speedometer of a car moving east reads 100 kilometers an hour. It passes another car moving west at 100 kilometers per hour. Do they have the same speed? Well, they're both going 100 kilometers an hour. Great, that's the same. What about velocity? Well, we should see one of those would be a negative velocity. They're going in opposite directions. So those are opposites, meaning one of the numbers there would be negative, and they would crash. Okay. During a certain period of time, the speedometer of a car reaches a constant 60 kilometers an hour. Now, does this indicate a constant speed? As long as your speedometer is accurate, I'm going to go with yes. And then you're going to think, well, if it's still going 60 miles an hour, how can it not have a constant velocity? And the question becomes, is it going straight on the freeway, or is it making any turns at all? Because if it turns, any turning, any change in direction when you're talking about a vector quantity is a change. So the velocity is actually not constant if that car is changing any direction anywhere. So if it goes around a bend on the freeway, that velocity has changed. All right, so velocity changes if speed or the direction of the motion change. So if you speed up or you slow down, or if you turn left or if you turn right. And the way to think about this is just think about yourself in a car. Okay, and think about yourself just driving in a car. If you're doing 80 miles an hour, 100 miles an hour, it doesn't matter. If you're going and you're not changing your velocity at all, you can sit in the car and feel like there's no change in your motion. You can sit up, you don't feel your seatbelt pulling on you, there's no change. But if the person driving the car suddenly accelerates, you get thrown back. That's a change in velocity. If they slam on the brakes, you get thrown forward. That's a change in velocity. But also, if they suddenly swerve right, you get thrown left, right? That is a change in velocity. And if they swerve left, you get thrown right. Again, it's a change in velocity. And you can feel those changes in velocity when you're in a car. Okay, so when we talk about a change in velocity, right, a change in velocity, we call that acceleration. And we're going to call even what we would naturally call deceleration when you slam on the brakes, that is just negative acceleration for us. That is still an acceleration. When you go around a turn, that is an acceleration. That is an acceleration. It is a change in the velocity. Okay, so we can give acceleration as a change in velocity over the amount of time that takes. And so you're going to see acceleration if your velocity is given in meters per second, the units, and your time intervals is seconds. Your acceleration is going to be given to you in a unit that's meters per second per second. Or we could do meters per second squared there. And that's just the acceleration. It doesn't matter if you're going faster, slower, all of that is given as acceleration. So, when an object speeds up, slows down, and changes direction, all those things are defined as acceleration. Okay, so here we go. We're going to start talking about free fall. If I had, what you're supposed to be imagining here on the right-hand side is a string holding together a bunch of balls. So you just have a bunch of balls attached to this string, and they're just suspended. And the string isn't pulling them or anything. We're just going to drop this, right? So we just have a string, piece of yarn, whatever, and some balls attached to it. And if we listen to the balls hitting the floor, they would hit faster and faster and faster and faster and faster. And we're going to look at why that is. We're going to look at acceleration due to gravity. We're going to know that it's constant, but there's something interesting going on where it actually speeds things up. Okay, so we're going to look at this diagram several times. So you might want to get it down and leave some room to the left of your paper and leave some room to the right, because you're gonna see this slide a few times. So when we look at velocity and free fall, this is just taking a ball and dropping it, all right? We're going to look at the acceleration due to gravity, and it is approximately 10 meters per second per second. So it's going to go 10 meters per second squared down. It's always pulling you down. Doesn't matter if you throw the ball up, it still pulls down. If you just drop the ball and it's going down, it's always pulling down. Gravity always pulls down. It's really 9.8 meters per second, but we can average it out to about 10 for almost all of our calculations, unless we need to be really specific. So if it is 10 meters per second going to increase the speed, then what you see as you look over at this ball that we're dropping here, right? In a second, it's suddenly going 10 meters per second, right? Because every second, we're going to increase by 10 meters per second. So the first second, right, at 0, it's stationary. It's not doing anything. By 1 second, it's going 10 meters per second. We're going to increase that by 10 meters per second, which means at 2 seconds, it's going 20. Then at 3, it's going to go 30. At 4, 40. At 5 seconds, it's going to go 50. You can see it's going faster and faster and faster. One thing you need to be aware as we talk about velocity and free fall, until we talk about terminal velocity, we are not taking into account air resistance for this. So these are going to be metal balls with minimal air resistance. I'm not talking about dropping a feather where I have a lot of air resistance. That'll mess up our math. All these experiments are going to be done with sort of heavy small balls where you have very little air resistance, and then you can really see the effect of gravity nicely. Okay, so now let's think about throwing a ball up in the air and letting it come back down. So you can see on the right, now if you think about a ball getting thrown up in the air, it actually stops when it hits the top. Right here, it's at 0. And you can see on the right-hand side that it does exactly what it did in that previous slide. It goes 10 meters per second faster, and then 10 meters per second even faster, so 10, 20, 30, 40. Well, let's think about how that applies as it goes up. It is slowing down by 10 meters per second every time it moves up. Remember, this gravity thing is always pulling down. So as we look at this ball going up, it goes right here, it's going up, but it is slowing by 10 meters per second. And it's getting even slower here. So as fast as you throw it, every second it's going 10 meters per second slower until it finally reaches a point where it's going 0. That's the top, and it's going to turn around and it's going to accelerate down at the exact same rate. Okay? So as we look at positions in free fall, and we start measuring the distance, all right, so now we were talking about the velocity previously. What we've added in on this slide is the distance it's falling, okay? So check this out, the distance, it's interesting. Our acceleration's accelerating by 10 meters per second down, if you remember your previous slides, right? These are going down, it's falling. But look at what happens to the distance. The distance goes 5 meters here, then 20, 45, and then 80. They get more and more spread out. And Galileo was actually the one who figured out this pattern. And if you can imagine trying to drop a ball and figure out where it is in midair, you would find that, fairly difficult. And Galileo realized that he can't just drop a ball and just figure it out, but he could put balls on an incline. And by putting them on an incline, they do sort of the same thing as if you just drop them, but they do it a lot slower, so you have time to figure out what's going on. And you can see by the positions of these balls that they spread out by that same ratio we just saw on that previous slide, right? They spread out, they just do it in a nice slow way, and it's easier for Galileo to study. All right, so Galileo actually made this thing called these clicking ramps. And what he found out was this bottom ramp, these clicks actually are the same time distance apart. So if you were to roll a ball, if over here, this side is the incline is up, right? And we're gonna roll a ball this way. These clicks actually come the same sound, the same timing apart, right? It's gonna be an even click, 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 click. Where if you rolled it here, we know from experience that they would actually speed up. He actually was able to figure out this ratio. And you can see it's actually an exponent. We're going to square this to get the distance, the time gets squared. But he was able to do that using ramps and then figuring it out and listening to the noise these balls made, which was, pretty clever. So, what did Galileo realize? Well, he realized that the distance, and you do need to write this formula down, and you probably need to put little stars and hearts around this so that you remember it, is the distance is going to equal 1/2 AT squared. That's how you're going to write that. Distance equals 1/2 AT squared. A is the acceleration due to gravity. We often just write G for gravity because it's so awesome. We give it its own letter. But that's plain old acceleration due to gravity. It'll be a G sometimes. You'll see that. Don't freak out. That's just acceleration. And then time squared. Remember I said he found that kind of awesome ratio going on. And it was the square of the time. That things speed up. They go faster according to the square of the time. So if we want to measure the distance here, as we release it, at that first second, it goes 5 meters, right? Well, that's 1/2 the acceleration due to gravity, which is 10 meters per second squared. And then the time is 1 second squared, so 1 times 1. All right. And then at 2 seconds, we're going to get 1/2 the acceleration due to gravity, which is 10. And then you get 2 squared, and you're going to find out that that's 20 meters. And so we see this exact ratio going on that was on Galileo's inclined plane. Okay, so gravity is accelerated at 10 meters per second. So when you hit 3 seconds, it does the math here for you. Distance fallen is 1/2 10 meters per second squared. And then 3 seconds squared, 3 times 3, and you get 45 meters. We'll practice doing a few of those. Okay, just for fun, if you want to see how fast your reflexes are, if you take a dollar bill and you hold your thumb and your index finger over Washington's head and have a friend drop it, theoretically you shouldn't be able to catch that, but just be careful you don't give any facial cues that you're about to drop it. If you're surprised, that should go faster. That should fall faster than you should catch it.